Hello everyone. So in this pre-lecture tutorial, I thought I'd walk you through a couple of examples of how to calculate the pH of a strong acid solution and also the pH of a strong base solution. And so the way really to get started with this is understanding that, again, if I'm going to calculate a pH, then based on what we learned in the last pre-lecture tutorial, I'm going to need to take the negative log of the hydrogen ion concentration. And so I'm going to need to somehow relate the concentration of the intact acid to the concentration of the hydrogen ion. And so the way to do this is to consider the dissociation process in greater detail. Essentially, if I have nitric acid, since nitric acid is a strong acid, then that means that I can expect the dissociation to hydrogen ion and nitrate ion to occur fully. And so that would mean if I have 0.00125 moles of nitric acid per liter because of this initial concentration, then if I consider the dissociation process for every 1 mole of the nitric acid, then 1 mole of hydrogen ion can be expected to dissociate. And so that means that my concentration in solution for the hydrogen ion would also be 0.00125 molar in hydrogen ion. And so with that in hand, I can just simply go and plug that in to this expression. And that would be negative log of 0.00125. And if I go ahead and do this math, then I get a pH of 2.90 for a 0.00125 molar solution of nitric acid. But what about if I wanted the pH of potassium hydroxide? If I go ahead and think of the dissociation equilibrium, potassium hydroxide being a strong base should dissociate fully to potassium cations and the hydroxide ion. But I can't use the hydroxide ion directly to calculate pH. But I can use some of the other relationships that I learned in the last pre-lecture tutorial. Namely, one approach I can take is to go ahead and calculate the hydroxide ion concentration from the starting concentration of my base. And so this solution is 0.00125 molar in potassium hydroxide. Now, again, considering the dissociation process, for every 1 mole of potassium hydroxide, then I will expect 1 mole of hydroxide anions. So that means that the solution will also be 0.00125 molar in hydroxide ions once the dissociation takes place fully. But what I can do is, with this concentration, I can calculate POH, because remember, POH is the negative log of the OH concentration, so I could do that. But then also, we should bear in mind that pH plus POH is 14.00 at 25 degrees Celsius. So assuming that we're at 25 degrees Celsius, we can use this equation to then convert from POH to pH. So solving for pH here, that means that pH is equal to 14 minus the POH. But the POH is the negative log of the hydroxide ion concentration. So the pH is 14.00 minus the negative log of the hydroxide ion concentration. Okay, these two negatives, when you multiply through, would become a positive, and I end up with the final equation of pH is equal to 14 plus the log of the hydroxide ion concentration. So now I've managed to derive for myself an equation where I can use this concentration of hydroxide ion that I calculated earlier. So going ahead and plugging in to this equation and doing the math accordingly, I end up with a pH of 11.10. So really, these problems that involve strong acids and strong bases involve using some of these relationships that we talked about in the prior pre-lecture tutorial, such as pH is equal to negative log of the hydrogen ion concentration, and pH plus POH is equal to 14.00. POH is equal to the negative log of the hydroxide ion concentration. It's also entirely possible, if I were to calculate this hydroxide ion concentration, recall that Kw is equal to the hydrogen ion concentration divided by the hydroxide ion concentration. So there's actually another possible way for me to actually do this problem. I could solve for the hydrogen ion concentration by solving for the hydrogen ion concentration using this equation instead, where, again, if I'm at 25 degrees Celsius, that would be 1.0 times 10 to the negative 14th, and you would divide this by 0.00125 molar hydroxide ion. If I do that math, then my hydrogen ion concentration becomes 8.0 times 10 to the negative 12th molar. And then if I go ahead and plug directly into the pH equation and take the negative log of 8.0 times 10 to the negative 12th, then I end up with a pH of 11.10 using that method for solving the problem. So notice that the pHs do match up as we would expect. And so these types of problems have more than one way to solve them. So go ahead and try the follow-up assignment. Play with different ways to solve them using the expressions that we've talked about in this particular pre-lecture tutorial. Again, if you have questions, by all means email. And again, we'll discuss this in class. Okay, so have a good night, and I'll see you then.